When people were busy speculating about the possible endings of the universe, whether it would end in a big crunch, heat death, or reach a state of equilibrium, a mysterious force revealed a fourth possibility. We might still be in the midst of a cosmic explosion known as the Big Bang. But what exactly is this enigmatic force that keeps tearing the universe apart? In the previous episode, we talked about how our scientific knowledge of the universe is far from complete. In fact, humanity's understanding only accounts for less than 5% of the entire universe. Within this 5%, there are still many unsolved mysteries. We call this the observable and studyable matter, while the remaining 95% includes 27% known as dark matter. We deduce the existence of dark matter through its gravitational effects, which means it has mass. However, besides mass, we have no way to observe or study this substance. Nonetheless, it's somewhat fortunate that we at least know this 27% is still composed of matter. However, the remaining 68% is an even greater mystery. Physicists call this portion dark energy, and you can imagine it as an immensely vast entity, but we have no idea what it really is. So why do we call it dark energy if we don't know what it is? Is it some form of energy? Well, in reality, this mysterious stuff is fundamentally different from the energy we are familiar with. In truth, you can call it anything you like. Now, since it's not matter and doesn't have gravity, and we know nothing about it, you might wonder if scientists just created this concept out of boredom. But that's not the case. There is one thing about dark energy that we can observe. It accelerates the universe's expansion. Its discovery was entirely accidental. Scientists were originally trying to measure the rate at which the universe's expansion is slowing down. However, they stumbled upon the surprising fact that the expansion of the universe is not slowing down at all. Instead, it's actually speeding up. Let's go back a bit. Initially, people believed the universe had always been the way it is now, with the size of space remaining constant. It seemed like a very intuitive answer, but the development of science has taught us that errors often hide in the most intuitive assumptions. Until a little over 100 years ago, most scientists even believed the universe had always been in its current state, and even the great scientist Einstein thought so. The idea that the universe could change was beyond most people's imagination. But one day, astronomers made some peculiar discoveries. They measured the light from stars and galaxies around us and found that everything was moving away from each other. This effect of moving away is observed through the redshift of light, meaning when an object moves away from us, the light it emits shifts towards the red end of the spectrum. However, it's crucial to understand that everything moving away from us doesn't imply that we are at the center of the universe. Imagine it like this. It's as if there are many raisins on a piece of bread, and as the bread expands while baking, each raisin moves away from all the others. No matter which raisin you stand on, you will find that all the other raisins are moving away from you. But none of the raisins is at the center of the bread. So, since it's discovered that the universe is continually expanding, it means that it must have been much smaller in the past. At some point in the distant past, the universe must have been incredibly small. Some physicists found this idea absurd and humorously named the universe model the Big Bang. And so, this slightly ironic name became the standard theory of the universe's expansion. Astronomers discovered the universe's expansion in 1931, which means the universe might have originated from an incredibly tiny point. Just try to imagine compressing the entire universe into such a small point. Its density would have been unimaginably high. One thing to note is that this point wasn't floating in some larger space. It contained all the space and time within itself. People refer to this infinitely small, infinitely dense point as the starting point, with nothing existing outside of it. Well, we understand how the universe began, but this might seem less important. However, since the universe is expanding, it leads us to wonder about how it will end. The answer lies in one of the four fundamental forces we mentioned earlier, gravity. When everything in the universe is moving away from each other, gravity acts in the opposite direction, pulling everything inward. Every piece of matter in the universe is being pulled by gravity. But what does this mean for the ultimate fate of the universe? People have come up with several different answers, which entirely depend on the amount of gravity within our universe. So, let's explore how much matter there is in the universe. There are three simple hypotheses we can consider. First, the universe contains a vast amount of stuff, and eventually, gravity will prevail, causing the expansion to slow down gradually. Everything will then start to contract back, and this scenario is known as the Big Crunch. The second possibility is that the universe doesn't have enough stuff, and gravity won't be able to slow down the expansion. In this case, the universe will keep expanding forever, becoming increasingly sparse and colder. This is called the heat death. The third option is a delicate balance, where the universe has just enough stuff for gravity to slow down the expansion, but not enough to stop it completely and start contracting. So, the universe will keep expanding, but the expansion rate will gradually approach zero. Now, since the universe started with a big bang and there are no other forces currently pushing it outward, only gravity pulling it back, we have these three possibilities to consider. Can you guess which one is correct? Sometimes, physics plays a grand joke on even the cleverest minds. All three guesses turned out to be wrong. The correct answer is the fourth possibility. The universe is expanding at an accelerating rate. But how do scientists know that the universe is accelerating in its expansion? To figure this out, we need to compare the speed at which other galaxies were moving away from us billions of years ago with their speed now. Predicting the future is challenging, but investigating the past is relatively easy for astronomers. The universe is incredibly vast, and light has a finite speed, so it takes a very long time for light to travel from distant places to Earth. This means when we observe distant stars, we are seeing light that is very ancient, allowing us to glimpse the distant past. By comparing the velocities of objects, where very distant objects move at one speed and closer objects move at another, we can deduce that the velocities of objects change over time. However, there's a problem. How can we differentiate between a dim star that's very close to us and a bright star that's very far away? When we look at them through telescopes, they both appear as faint little dots, and we can't send spacecraft to see how far away they really are. This dilemma persisted for a long time until scientists discovered a particular kind of star that behaves identically anywhere in the universe. These stars grow at the same rate and, when they reach a certain size, they collapse inward and produce a massive explosion. Scientists call these stars Type Ia supernovae. The crucial aspect is that these Type Ia supernovae all explode in the same way. So, after proper calibration, if we see a Type Ia supernova that appears dim, it must be far away. If it appears bright, then it's closer to us. It's like having many lighthouses in the vast ocean, and we can determine their proximity by observing their brightness. Astronomers call these Type Ia supernovae standard candles. Knowing their distances, combined with the redshift effect we discussed earlier, allows us to calculate the motion speeds of these objects. This means astronomers can measure how the universe's expansion rate changes over time. At that time, two scientific teams competed to be the first to measure the varying expansion rate of the universe. Naturally, they were still considering the first three hypotheses we mentioned earlier. Both teams assumed that the expansion rate of the universe either slowed down or remained constant. But to their confusion, the truth turned out to be the opposite. Compared to the past stars, those closer to us are now moving away faster. In other words, the universe's expansion is accelerating. This led to the conclusion that there must be some mysterious force pushing everything in the universe outward, and this force is even stronger than the gravitational pull of all the objects in the universe combined. The actual calculations show that the universe's expansion did indeed slow down in the beginning, but in the recent 5 billion years, the universe has been accelerating its expansion. Scientists call this driving force behind the accelerated expansion dark energy. Similar to dark matter, we can't see it, but it pushes everything outward, so scientists call it energy. Through calculations, scientists have determined that dark energy accounts for about 68% of all the matter and energy in the universe. Besides inferring the ratio of dark matter and dark energy by observing the changing expansion rate, we can also study the current structure of the universe to deduce their proportions. The observed arrangement of planets and galaxies in our universe has a particular pattern. By using computer simulations, scientists can backtrack from the current state of the universe to the end of the Big Bang and determine how much dark matter and dark energy would be needed to create the universe we observe today. If you don't set the appropriate proportion of dark matter in the simulation, you won't get the observed galaxy shapes or their formation times matching reality. The immense gravity provided by dark matter helps ordinary matter clump together, and galaxies must have had this much dark matter during their early formation. On the other hand, dark energy keeps pushing things outward, allowing our simulated universe to align with the real universe's timeline. If you mix dark matter and dark energy in the simulation, that is, if you assume dark energy doesn't exist and dark matter accounts for 95%, you won't get the same results either. Besides these methods, scientists have many other ways to calculate the proportion of dark matter and dark energy, but let's not delve into all of them. Regardless of the approach, the proportions of regular matter, and dark energy are approximately 5%, 27%, and 68%, respectively. Alright, now we know the proportion of dark energy and how scientists discovered it. But what exactly is dark energy? All we know is that it's a force driving the expansion of the universe, but apart from that, we know nothing. Currently, the prevailing view is that dark energy originates from space itself. People generally think of space as the opposite of matter, and in some regions between galaxies, there's only space, devoid of matter and even dark matter. Now, imagine if there's energy present in this seemingly empty space, it could provide a push, causing the universe to expand. This might sound bizarre, but it actually has some scientific rationale. In quantum mechanics, there's a concept of energy fluctuations in empty space. According to quantum mechanics, at the microscopic level, objects can do things that macroscopic objects cannot do. For example, they can have an uncertain position. That means an object can appear differently when observed and when not observed. Similarly, according to quantum physics, in a very tiny space, particles can suddenly appear from energy and then convert back to energy. Since quantum mechanics already stretches our imagination, why can't we accept the idea that seemingly empty space is, in reality, filled with energy that can push the universe outward? However, this explanation has a problem. When scientists calculate how much energy should be present in space according to quantum mechanics, they arrive at an enormously large answer. This answer is 10 to the power of 60 times greater than what quantum mechanics predicts, which means it's a 1 followed by 60 zeros, a number too vast to fathom. To put it into perspective, it's estimated that the entire universe has around 10 to the power of 85 particles, and this calculation exceeds that number by a factor of 10 to the power of 60. Clearly, this is way too far-fetched. There are other explanations for dark energy, such as a new type of force permeating space or a special field. These theories come in various versions, but they all share a common feature: they are challenging to verify. Some of these hypotheses involve fields that do not interact with our regular particles, so we can't detect them. Others may introduce new particles, but those particles would have masses far beyond our current measurement range. All of these theories are in their early stages of development, which means there's no standard answer yet. Now, after learning about dark energy, when we look back at dark matter, it seems more approachable. At least, we know it's some form of matter. Physicists don't necessarily have to fully understand dark matter before studying dark energy. It's just that we have fewer clues about dark energy compared to dark matter. As we mentioned in the previous episode, studying dark matter will undoubtedly lead to groundbreaking discoveries that could influence the behavior of ordinary matter in our reality. Researching dark energy will likely bring revolutionary and paradigm-shifting discoveries as well, which is good news for us, but the existence of dark energy also brings some bad news. If the universe keeps expanding faster and faster due to dark energy, everything will move away from us at an accelerating pace. As the expansion continues to speed up, the objects in the universe will eventually be moving away from us at speeds exceeding the speed of light. You might wonder, doesn't Einstein's theory of relativity prohibit anything from moving faster than light? Strictly speaking, Relativity forbids any information carrying speed from exceeding the speed of light. However, an object's velocity moving away from us doesn't carry any information, so its speed exceeding the speed of light doesn't violate relativity. If this hypothesis is true, it means that one day, the light from any star won't be able to reach us anymore. At this moment, the number of stars visible in the night sky will surely diminish compared to yesterday. People speculate that in billions of years, we might only see a few stars in the night sky. Many more years later, the night sky might turn completely dark. Of course, at that time, whether human beings still exist, or in what form, is uncertain. After all, we're talking about billions of years from now. If the universe reaches that point and develops a new civilization, they would believe that there are no stars in the universe, and there would be no astronomers to imagine such things in that civilization. That future civilization would be quite lonely. However, keep in mind that human science has only been developing for a few centuries, and we are making predictions based on existing data. We can't say for sure whether the universe's expansion rate will slow down again someday, and perhaps by that time, we still haven't figured out what dark energy truly is, and it mysteriously disappears. Alright, we've spent 2 sections talking about dark matter and dark energy. Now, let's return to the familiar 5% world of regular matter, as that's the place we understand the best. Speaking of which, there's some bad news to tell you. Even within that 5% we can observe and study, there are still plenty of mysteries to be solved. One of these mysteries is about the most fundamental particles of matter. We'll delve into this topic in the next section. See you in the next episode.